So I was supposed to actually talk about black hole a little bit systematically, like to drive, or at least to talk about the metric from starting from Einstein field equations, and then we can discuss it systematically. But I think we had already too much, so maybe it's time to talk about some interesting still topics about in a less maybe mathematical way, although there are very important ideas and a lot of interplay between quantum mechanics and general relativity in this topic. So in this lecture, we are going to discuss quickly some, of course, some aspects of the classical black holes, and then we are going to discuss some features of its quantum effects. I'm not going through GR since Alexei already did a great job covering this. And then maybe I will just go through Schwarzschild solution, like what are the features and properties of these solutions and what we mean by black holes, okay? And then I'm going to state hawking the arguments, why this is this information loss paradox is a problem for us, or what it points exactly. There are some resolutions or explanation for this, which is the black hole complementarity, and then there is the more recent work, which is the firewall argument, which is saying basically that the complementarity is not waterproof, or is not really can be considered as a resolution for the black hole information. And I'm not sure I will go through this. All what I need from this talk is just to lay down for you the paradox itself, try to understand it and see what is the issue here. So let me start. Of course, you know GR now. So this is Einstein field equations, which is very similar to Poisson's equation in the sense that on the left-hand side you have a fundamental quantity which we call the field, which is the metric, and you have derivative on it. This is what constructs R mu on R. Okay, this is very similar to the left-hand side of the Poisson equation, and to the right-hand side we have sources. Okay, so what we are going to deal with is a solution for Schwarzschild, for Einstein field equation, which is symmetric, and it is vacuum solution, which means that we don't have any sources. Okay. So if I try to put this constraint of symmetry on the metric, okay, what I can write from requiring spherical symmetry is the following. I can have two pieces, let's call them f of r. This is an arbitrary function, and another function which is g of r, dr squared plus r squared d theta squared plus sine squared theta d phi squared. This is the most general form for spherically symmetric metric, okay? Which means that you have, even when I have sources, okay? I could fill my space with some matter And this matter is spherically symmetric. That's to say, I can think of it like layers of matter concentrated around some point. Okay? So this is also described by this metric. This is the most general spherically symmetric metric. You can write down, okay, in 4 dimensions. Okay? But in our case, we are going to take T mu nu to be 0. So we are describing this in vacuum. Okay? So generally, we speak of some source which is very, very small or tiny, point-like source. Okay? And we don't care about even writing it as a direct delta function on the right-hand side. But we solve for the external region. And the solution for external region is going to fix for us the function f and g. Okay? And this is the form of the function f and g. This is the form of the metric which satisfy Einstein field equations. Okay? So directly you can see certain properties for this metric. First of all, if you actually study this metric very far away, that's to say r, this parameter r, which is basically the radial coordinate in this description. If we take r to very large values, what you will get? You have here 2m over r, and here 2m over r. So these quantities are going to be very small, right? It's going to be basically 0. So you have here just minus dt squared plus dr squared, and then r squared and the rest. And what is that? Can you recognize that? Can you recognize this metric? This is Minkowski, right? This is a flat Minkowski metric. Okay? So it means what? It means actually when I go very far away from this solution, from the center of this solution, I get flat space. Okay? This is why this solution, we call it asymptotically Minkowski or asymptotically flat spherically symmetric metric. Okay? So this is one thing. The other thing is that you can see that there is a problematic value of r here. So if you put r equals 2m, you get very strange thing in this metric. For this component, you get 0. For this component, it blows up. Okay? So you would say directly that this point, or this actually surface of constant r, is problematic. Okay? And in fact, this is not true because if you study this metric carefully, you would see that this value of r is nothing but a coordinate singularity. And in GR, we differentiate between two important concepts: coordinate singularity and curvature singularity. Coordinate singularity, it means it's a bad point for the coordinate. One of the things that we learn in GR or in differential geometry in general, that you cannot have one coordinate system which covers the whole space-time. You need to have multiple of them in order to cover it in a smooth and nice way. Okay? So here, this point r equal 2m is a coordinate singularity. It's just a bad coordinate. I might change the coordinate into something else, and this point is not going to cause any problem. Okay? Very similar to the spherical polar coordinate. Remember, when we write spherical polar coordinate here at r equals 0, this is also a problematic point. From the point of view of just apparently here in the metric, it's problematic. But you can go to Cartesian coordinates, x, y, and z, and you see nothing is problematic about it. So this value is like that. It is a coordinate singularity, but it has some other property which is far more important, which is it is a horizon, okay? And we are going to define what we mean by a horizon later. But in order to continue our discussion about coordinate and curvature singularity, we can actually detect here also that there is a curvature singularity in this matter. And the way to detect curvature singularity is to calculate curvature invariance. What we mean, I mean, there are many ways to detect curvature singularity, but the simplest way, the simplest among them, is to calculate curvature invariance. What we mean by curvature invariance, scalar quantities made from the curvature tensor. Okay? For example, Ricci scalar. This is one thing. Ricci tensor squared. Another thing. And the Riemann metric squared. These are the simplest possible. There are also the Weil square tensor. Okay? You can construct this. And if you find that there is a singularity in any of the coordinates, this means that you have a curvature singularity. For example, in this case, if you calculated this quantity, okay? First of all, these two quantities are going to be zero. Why? Because we are solving G mu nu equals zero, right? And this is R mu nu minus half G mu nu R is zero. So when you contract, it is proportional to R. So this means R is zero, and you can see since R is zero here, R mu nu also is zero because the addition is zero. So these two quantities are zero, but this quantity is not zero. You'll find that actually this quantity is proportional to this constant mass to some power here divided by R to the 6, which means that at R equals zero, this quantity blows up. So indeed, this is what we call curvature singularity. At this point, at R equals zero, there is something strange happened here to the space-time. In fact, at this point, the space-time is not really well defined. Okay? So this is what we call singularity. Okay? And I'm not going to talk about singularities more than what I have already said. So this is just, as I said, to differentiate between coordinate and curvature singularity. Now we come to what we mean by a horizon. So let's suppose that we have an actual star. So first of all, a horizon is what we defined here. So it is the surface, okay, at which the radius is equal to 2m. Okay? So this defines a sphere of radius 2m. This sphere is what we call the horizon. Of course, it's a sphere around what? Around the center or equal 0. Now, this horizon actually has very strange properties. So, in this horizon, if you send a ray of light, you will find actually that this ray is getting absorbed and it won't be able to actually get out of the of this object at all. So let's try to imagine what happened for a star, for a usual star, okay, when we try to compress this star more. We try to actually reduce the volume of this star. Of course, we increase the density when we do that, okay? And in fact, we don't have to do this because gravity is doing this, okay? So we are just describing what happened when a star really collapses. So in this case, this is the surface of the star here, okay? And I just exaggerated the size of the Schwarzschild radius. I make it big enough to see. And then when the surface of the star, when the star actually collapses, of course, its radius is getting smaller and smaller till it goes inside the Schwarzschild radius. But once it goes inside the Schwarzschild radius, it cannot go up with any force again, cannot increase the size. It will go and shrink, okay, to a point. And this point is what we call the curvature singularity here at r equals 0. Yes?
Doctor, is this point at r is equal to n, it's like a critical point, like Professor Benjamin described?
In what sense it's a critical point?
Critical point that there's a phase, and then before 2m, or greater than 2m, and then another phase.
Right, but I mean, in the context of statistical mechanics, a critical point has a very precise meaning. Okay? A critical point is a point at which we have a continuous phase transition. This is what he meant. Okay? But if you mean that there is difference inside and outside the system, which we call the black hole, yes. So, in fact, the physics inside of this horizon is completely disconnected from the physics outside of this horizon. Why? Because there are no rays of light which can actually escape from this surface here. This surface is what we call a null-light surface. So if you send a ray of light from inside, try to actually let it escape outside, it won't be able to do that. It will bend on itself and come back to the inside again. Okay? Yes?
Are they really disconnected? Because, like, the outside
They
can
are
influence-
causally disconnected.
But the outside can influence what's
Of course.
inside.
So what I'm saying, that inside
Cannot,
cannot escape to the outside. Okay, but of course always it's like one-way membrane. Okay, you can go in but you cannot come out. Okay.
So a critical point, or
So it's not really critical point in the sense, of course, of the statistical mechanics, but it is a surface beyond which the physics is different. Okay, we will see actually some properties of this surface later on, even quantum properties. Okay, so let's have a semi like definite definition of what we mean by a black hole or a horizon, in fact. So any object with horizon, with event horizon like this one, we usually call in gravity a black hole. Okay? And it doesn't have to be point-like. It could be actually any shape. It could be cylindrical. And this, in this case, the singularity is not going to be a point, it's going to be a line. Okay? Just to extend the concept for you. But a black hole is a region of space which has very strong gravitational field, okay? Such that any light ray emitted from its surface cannot escape its gravitational pull, okay? So any light ray emitted inside or at the surface, okay, cannot escape its gravitational pull. So this is what we mean by a black hole. So in fact, black hole has history because general relativity was not the first theory which predicts the existence of black hole, but even classical physicists like Laplace and Mitchell actually they recognized that we could have a star which is heavy enough to the extent that the escape velocity of this star or of this planet is exceeding the speed of light. And if it exceeds the speed of light, it means that nothing can escape out. Okay? So this idea is not, as I said, recognized in general relativity. In fact, Einstein didn't believe in the existence of black holes. He thought that this is not a physical system. You cannot form a black hole somewhere, okay? Because there are lots of physical problems toward its construction. So this have affected actually the opinion of physicists till actually 60s. But before 60s, I think in 40s, people start to realize that these objects could form, especially after an important calculation by Oppenheimer and Snyder. Okay? They actually calculated that we can have a form of matter which can collapse, spherical symmetric matter, which can collapse into a black hole. Okay? So it shows that you can form a black hole from a physical situation. Okay? But even during the 40s and 50s, people thought that you can form these types of weird solutions or weird systems because of the very high symmetry of these solutions. But if you perturb it, or if you deviate from this spherical symmetry, you might not have this black hole at all. But actually this was not correct. Okay? So later on, our research showed that this is not the case. In fact, black holes are, or spherically symmetric solutions in general, are kind of stable around perturbations. Okay? Especially black holes. Yes.
Next question, just to go through electromagnetic, any sort of might call it electromagnetic impacts for matter if you have a sharp matter, there might be a collapse of the action of electromagnetic actions in matter. Because electromagnetic.
How?
I don't know. Actually, I don't know. I know that there are some people who have done
This
some
happened in
research.
gravity, yes. If you try to compare between Coulomb force and general,
I know that the electromagnetism is much stronger than the gravitational force by think or something. But why the electromagnetic? Why people didn't talk about the collapse of matter under the action of electromagnetic interactions?
because electromagnetism has positive and negative charge, so they compensate each other. This is why in gravity we don't have shielding effects, but in electrodynamics we have shielding effects. Okay? You cannot shield gravitational field at all, but you can shield electric field. You have Faraday cage, for example, but you cannot shield gravitational field. It's going through everything. Anything with energy or mass will gravitate. Okay? So there are actually very important theorems in gravitational physics which shows that for black holes we have very specific quantities which we can observe. Okay? So these specific quantities are mass, charge, and angular momentum. So this actually reminds us with elementary particles. In some sense, which is very vague, of course, it says that black holes could be like comparable with elementary particles, but it is an illusion. But in any case, in general, black holes in Minkowski space, at least, are characterized by mass, charge, and angular momentum, which means that the only observable physical quantities we can actually really watch or observe out of these black holes are these three quantities. Okay? So this is just a sketch which shows us very important picture of how this collapse happened, because it's very important to keep in mind that this surface that we call horizon, okay, is like a limiting surface, which is telling us that if you are an object enfolding inside this black hole, there is no way to escape. You can see here these are light cones, and light cones shows that the possibility of going in different directions. For example, in Minkowski space, this is t and this is x. When I drew this cone here, so let's suppose that we are here at certain time and at certain position. This is the future of our evolution, okay? This is a future light cone. This is a past light cone, okay? So this point here could affect anything, any later point here, okay? Because of this light cone. This is the cone of causality, in a sense, okay? Any point here in this light cone could got affected by the existence of this point, okay? So you cannot escape to this region, for example, or you cannot evolve to this region, okay? Because in order to do that, you need to actually go with a speed more than the speed of light. So the same thing here. So the light cones, when you go closer to the horizon, is going to tilt in such a way that you can see that even when you escape in the other direction, you will just escape in the same region again. You won't be able to go out, okay? So you cannot escape. So this is how you should, in fact, observe the collapse, okay? From different points around the surface, which we call horizon. Then, in fact, in the 60s, we started to have some laws which we call black hole mechanics, or black hole laws, which were very similar to thermodynamic laws. But people were realizing that this is just an analogy, because simply how a black hole could be analogous to thermodynamics, okay? So you can see that reading this correspondence or reading this analogy, we can see that the internal energy is similar to the mass, the temperature is similar to the surface gravity, and this surface gravity is nothing but the gravitational acceleration on the surface of the horizon, okay? This is what we mean by surface gravity, like G, but on the surface of the horizon. And A is the radius of the, the area of the horizon, and it corresponds to the entropy, okay? And then the rest of the first law is about work terms, as we know. But we could have plenty or different work terms like phi dq, okay? Or rotation work terms like omega dj, for example, where omega is the angular momentum and j is the omega is the angular velocity and j is the angular momentum. And we even have something similar to the second law, which is saying that the area of the black hole is always increasing, which means that when we have a collision, for example, between black holes, this area cannot decrease in the collision, always increasing, okay? Which is reminding us with the entropy, which is always increasing. To the extent that in 1972, actually, Wittgenstein showed that in order to have a consistent notion of entropy in gravitational physics, okay, for a black hole surrounded by some gravitational systems or gravitation matter distribution, for example, okay, in order to have a consistent notion of entropy, the black hole should have an entropy which is proportional to the area of the horizon, okay, from just some thought experiment. He showed that, okay, and of course people were even not taking this also seriously, because having entropy excuse me, and having something like Ferris law with entropy and temperature, it means that we are talking about thermal equilibrium. We are talking about thermal system. But can a black hole be thermal? Can a black hole be a thermal system in equilibrium with its surrounding? Cannot be, right? Because it's like a big vacuum machine. It takes everything inside without giving anything. So we cannot have some kind of thermal equilibrium between this system and its surrounding. So this is why people didn't take this seriously. We'll take it just as an analogy. Till Hawking came in 1975 and have done a very important calculation. This calculation changed everything. So what he did was actually he considered a quantum field, like a scalar field, for example, around the black hole, okay? Or in the background of the black hole. So he had Schwarzschild metric as a background metric. That's to say, he's not going to quantize gravity. It's just taking gravity as a background, okay, field. But he quantized the scalar field in this gravitational background. And he actually tried to calculate certain quantities in this situation, and he was able to see that black holes are emitting particles like black body. So for an observer very far away from the black hole, this observer receives actually Planck radiation from the black hole. Okay? And the only observer sitting very far away from the black hole can see that, or stationary with respect to the black hole. If you are freely infolding into the black hole, you won't be able to see it. Okay? So it's only if you're sitting at a distance, okay, from the black hole and standing still. You are not moving. In any case, he was able to show that this temperature or this black hole is emitting Planckian radiation or black body radiation with a specific temperature. Of course, we know that from black body radiation, the curve of the black body is just one parameter fitting curve. The temperature can fit the curve. Okay? So it has to have some temperature, and this temperature is what we call today Hawking temperature, and it is equal to 1/8 pi Gm. Okay? Of course, there are other constants here which I set to 1. For example, if I write it correctly, it's going to be, there is h bar upstairs and there is k Boltzmann downstairs. Okay? And there is c to some power floating in the expression. But the important thing, there is h bar upstairs and there is Boltzmann constant downstairs, which is telling us that this temperature is a quantum phenomenon. It's a quantum effect. Because if you send this h bar to 0, temperature is not there. Okay? So this is a pure quantum effect, coming from the fact that we are quantizing this scalar field in this background of black hole matter. Okay? But how come we have this radiation? How come we have such a radiation? Okay? For this piece of physics, let me take you back to something simpler, and maybe we can try to understand the physics of this emission of Hawking radiation. So, I don't know if you have studied in modern physics or in condensed matter physics or solid state physics, there is some effect which we call field emission. Anybody heard that before? Or sometimes called emission? No. Field emission is very simple effect. You know photovoltaic effect, photoelectric effect? Okay. Photoelectric effect usually happen for alkaline material or metal, for example, and you hit it with photon, and then you get some electron. Okay? And we explain it through some work function of this material and stuff like that. Now, if we take the same material and we do the following, we apply very strong electric field, what is going to happen? What happened is that the electric field is going to be strong enough to pull out electrons out of the solid. It's overcoming the work function and is pulling out electrons out of the solid. This is what we call the field emission. Okay? So field emission is very simple effect. Okay? There is another effect also in quantum field theory which is very interesting effect. It's called Schwenger effect. Okay? And this effect is the following. If you try to, we will do actually a very similar thing, but not to a metal, but actually to a vacuum. We have a vacuum, a complete vacuum. Okay? We have a vessel, we evacuate it from air and from everything. We have a complete vacuum here. Okay? Then we apply a very strong electric field. But this electric field is really strong. Amazingly strong. What happened? What happened is that electric field is going to make the vacuum unstable. The complete vacuum unstable. To the extent that we have electron positron going out of this vacuum. So what happened is that actually this is telling us something very important, that our notion of vacuum in quantum field theory is very complicated. Vacuum is not a nothing. It is a system which have almost all particles, but they are خلايا نايمة. They are sleeping particles. And if you provoke them with some effect, like electric field, gamma ray, or whatever, they start to actually come up to life. Okay? So this is a very important effect that we know today, and we didn't actually verify this effect experimentally yet. But some people claim that they have verified, or they have seen this in graphene, because there are some analogy between many quantum field theory phenomena and graphene sheets in 2 dimensions. Okay? So they were claiming that they have seen something very similar to Schwenger. Yes?
How strong electric field are? Like what or
No, it's, I think it's very high. I think maybe 10 to the 10 volt per meter, something ridiculous. This is why we didn't achieve it yet. And some people also were saying that even before this strength, we'll start to have pair creation. Okay?
Are these particles virtual?
No, they become real. So vacuum is full of virtual particles. Okay? They are created, annihilated, and within the uncertainty limits that we cannot detect them or see them. But when we do something like that to provoke them, they come up to life. We can detect them. Okay?
So this is the difference between this and Casimir effect.
There is?
This is the difference between this and Casimir effect.
Yes. This is not Casimir effect. Casimir effect is
Pressure work.
you have a gain vacuum and you have two plates, two metallic plates in front of each other, and you observe the force, an attraction force between them. And I think this has been observed. Casimir has been observed. Okay? But this one not. Okay? So why I was discussing this? Because it's very similar to what Hawking radiation is about. So Hawking radiation here on the horizon, okay, our gravitational field is strong enough, okay, to start to make again the vacuum unstable and start to create pairs of particles. But one of them is going to escape to infinity, and the other one, which is the unlucky one, is going to go inside. This is why from a distance we see all sorts of particles coming out of this black hole as Planckian radiation or as black radiation. Okay? So this is what we call Hawking effect, and it happens at certain temperature which is related to the mass of this black hole. Okay, it goes like 1 over the mass. So the larger the mass, the smaller the temperature. And the smaller the temperature, the larger the mass. This is why people were searching for microscopic black holes. Because if we have microscopic black holes, this Hawking temperature could be detected. Because with these astronomical masses, this temperature is ridiculously small. In Kelvin, is really ridiculously small. Okay? So we come to the issue of information loss particles. So the idea is that because of the fact that we have Hawking radiation, and this radiation really is completely thermal, which means that it carries no information. It does not have just very uncorrelated, and it carries no information at all, okay? Because it's the simplest possible kind of radiation. So the idea is that imagine that we have constructed a black hole out of some matter which carries a lot of information or a lot of entropy, okay? And then when we formed the black hole, we waited, okay, till this black hole starts to radiate, and it keeps radiating Planckian or black body radiation forever. And when it radiates, by the way, it loses energy, and it loses mass, and shrinks. It keeps doing that till it vanishes. So where the entropy goes, or where actually the information goes, okay? So this was actually the puzzle. And this was a little bit confusing for many people at the time, because they were, including Hawking, because they thought that there is something wrong with this picture. Or maybe, since we are trying to merge two different theories, like quantum mechanics and general relativity, maybe we should modify one of them in order to be consistent with the other and try to make something which make more sense. So he was suggesting at the time that maybe quantum mechanics need to be modified in order to accommodate general relativity or gravity. Okay? So this is just basic quantum mechanics, which I know you know that very well. So let me actually try to be more specific on explaining the paradox here. Okay? So the idea is that in quantum mechanics, we have actually two notions. And maybe I should start with differentiating between two notions of states, what we call the mixed states and the pure states. Okay? So a pure state is the states that you are dealing with in quantum mechanics, which is basically a linear combination of certain bases, like energy bases, angular momentum bases, or something. But there is another important notion, which is very important when we deal with quantum statistics. And this is called density matrix. And the density matrix is a notion we need really when we have a sample, when we have a system, and this system can be divided into small subsystems. Okay? And each subsystem is in a specific state. Okay? Let me call this state a state which is related to whatever subsystem here. So alpha 1 is related to 1, alpha 2 is related to the subsystem 2, and so forth. Okay? In general, the states for these different subsystems could be different, right? So if it's different, it is described, okay, by what we call density matrix, and it is the sum over all these i's, all these subsystems, okay, with some weight, omega I, and it is the projection operator in this way. So if you want to represent rho, for example, in position basis, position representation, you multiply it with x and x on both sides, and in this case, rho as a function of x is going to be the sum over omega I psi I star of x psi I of x. Okay? It's going to be like that. Okay? So of course, this is like a small probability amplitude for each specific subsystem. Okay? So this notion of density matrix is very important when you have, as I said, a sample of states or a collection of states that you can divide, or a system which you can divide to subsystem. Each subsystem has its own state. Okay? You describe it with its own wave function, for example. Okay? So there are certain properties for this density matrix, and one of the important properties of this density matrix is that if you want to take the average of some quantity, okay, like quantity, physical quantity, which is represented by an operator O, and you want to take an average, this average is nothing but the trace of O with rho. Okay? You can show that. Another important property for the density matrix is that the density matrix rho is Hermitian, and the trace of rho is 1, okay? And for pure states, you have rho square is equal to rho, okay? So, to give you just an example, so for example, we can have rho which consists of certain eigenvalue like lambda 1, lambda 2, and so on, okay? And keep in mind that these lambda I should be between 0 and 1 because it has to sum up to 1, right? Its trace is 1. So this means the constituents has to be less than 1. Okay? And you can use rho also to represent pure states. Okay? When this happens, when you have one of the lambda is 1 and the other is zeros. Okay? In this case, this rho represents a pure state, like some psi, which is a linear combination of some bases. Okay? So rho here can actually also measure for us some sort of entropy in the system, which we call von Neumann entropy. And this entropy is because, of course, we deal with this rho when we have a statistical mechanical notion in quantum mechanics, right? So this entropy is going to be minus k Boltzmann trace of rho ln rho. So for a pure state, when you have rho which is just 1, 0, when you calculate the entropy, you'll find it 0. Because the trace, of course, because you will find actually that this is going to give you 0. Okay? And it's going to give you maximum when you have a matrix with dividing it like if you have n by n matrix and you have 1 over n outside and you have ones here on the diagonal. So when you calculate the entropy in this case, you will find it is k log n. Okay? Very similar to the statistical mechanical entropy. Okay? So why I'm saying that? Because in general, we use this notion of density matrix to describe a mixed state for us. A state which is have some entanglement. Okay? And we know in quantum mechanics that the unitary operator always take a pure state to another pure state. This is a very important notion. So if we have a unitary evolution and this unitary evolution is acting on pure state, the result has to be a pure state. Okay? So why this is relevant? This is relevant because let's imagine that I'm going to construct the collapse of this black hole from pure states. Okay? I'm going to have particles in its, for example, energy eigenstates, and these particles, I'm starting from that. Okay? Let's suppose that these particles are very, very far away from each other. Each particle I prepare is actually in energy eigenstate. Then I let this particle collapse by the gravitational field, and then they form a black hole. Then the black hole is going to emit Hawking radiation. This emission is, okay, these radiation are in mixed state. Why it's mixed? Because they are entangled. The photon which is going out here is entangled with the one which is going in. Okay? So this means simply that there is no unitary evolution which can link a pure state that I started with the mixed state that I ended with. Okay? So, what is the evolution then? I mean, if I cannot describe this evolution by a unitary matrix or unitary operator, does this mean quantum mechanics applied in this situation is not unitary? Or there is something wrong with the application of gravitational fields to quantum mechanics, or what exactly is wrong here? Okay? This is the information loss part. Okay? That we want to understand how this happens. People were saying that maybe this mixed state that you have seen in Hawking radiation is just the initial situation. And maybe later on, okay, you will start to have some sort of radiation, okay, after certain times, which is correlating these quanta or these particles with the particles which have fallen inside, okay? And this is called the complementarity, okay? And there are other resolutions or other trials to resolve this issue, but none of them so far is satisfactory, okay? Or fully, I have to stress on this, none of them is fully satisfactory, okay? So this is the issue, that we can start from a collection of pure states, which collapses into a black hole. Then this black hole surely is going to Hawking radiate, but Hawking radiation, since it is Planck radiation, it's composed of mixed states, and if keep doing that forever, how can we do this connection where U is unique? Okay? Of course, we know that any quantum mechanical system is described by unitary evolution. Okay? So, unitary evolution cannot connect between a pure and mixed states. And I'm leaving this problem to you to think about. Okay? Any question?
Are there any attempts for non-unitary quantum mechanics?
Are there
Any attempts for non-unitary quantum mechanics?
non-unitary quantum mechanics? I think so. There are people who are trying to do non-Hermitian quantum mechanics, and I think maybe it is by construction non-unitary also, but I don't know how much this is successful and accepted in the scientific community.
They also try some nonlinear corrections to Schrodinger equations.
Non-linear, yes.
Yeah, which is also non-unitary, of course.
Of course.
Yeah.
And these trials from the time of de Broglie, for example.
Yes.
He was the first one tried to do that.
But they have their own problems.
And every great physicist, at least once, he tried to do that. The non-linear correction of quantum mechanics, and failed, including big people like Steven Weinberg, Steve Adler. I mean, many people tried to do that. But
why
it
is
seems
it
quantum mechanics is quite rigid system that it's very difficult to even like modify a little bit. There's another question.
There's two matrix description. Yeah, project operator. Generalized version of project operator.
Yeah, I have projector operator, but we can use projector operators to do so many things. أنا قصدي أقول يعني أي operator أنا ممكن أكتبه كبروجيكتور operator.
Okay, I know this one. Yeah, projector.
خلي بالنا بس. Let's be careful here because of these eyes that I wrote. These are not the basis eyes. Okay, they run over the number of subsystems, and this number could be anything. Could be less than the number of bases, could be more than the number of bases. It's not constrained. Okay? But it is very important notion that usually is not taught in our quantum mechanics classes, but it is very important. The notion of density matters. Okay? Yes.
Why a free-floating observer will not see any radiation? Why a free-floating observer will not see any radiation?
Good. So this is from the equivalence principle.
This is it.
Yes. So how can I explain this? Does a free-falling observer can detect any gravity? So
This is radiation. You can detect radiation.
it is connected to the gravitational field in some sense. So I would, the way I might explain this is there is an equivalent radiation to Hawking radiation. It's called Unruh radiation. And this radiation is, actually you see it when you go with a spaceship and accelerate in the space. So if you go in the space and accelerate, you would see this Unruh effect. And it's very much like Hawking effect. You will see huge number of particles, like from Planckian distribution also, with certain temperature. And this temperature is nothing but the inverse of the acceleration of your spaceship. Okay?
I think a free-floating observer is an inertial free.
A freely falling observer is an inertial film which doesn't see any gravity. Right?
But if I'm very far away from the black body, I am an inertial free.
No, but you see, this is why I said either to be far away or even close to the black hole but stationary.
Still inertial frames. So when
Right.
observing radiation in another inertial frame, not observing.
Right, because of the equivalence principle, it's very similar that the observer which is freely falling doesn't see any gravity at all. Okay? It's just the equivalence principle. Okay? Any other question or comment?
I wanted to ask about the effect of when you're coming very fast. Does that have to do
With acceleration, not very fast. With acceleration. It has to be acceleration. Okay? So this is what happened closer to the horizon, because closer to the horizon here you have a constant acceleration which is like the G on Earth, but on this surface here. Okay? So this is why you see radiation. Okay? Any other question? Okay. So see you.
انا عندي اسئله بس من المحاضره بتاعت الجايه.
تمام.
بالنسبه للنورماليزيشن
اه
الكوانتيتيز اللي احنا قايسينها زي الالكتريك تشارج اللي هي